Who the math? Who the math? Who the math? Who the math?
Plus, sign, multiply, subtract, and divide. Get math in your mind, then you'll see your dollars rise. Teachers, have your kids play video games, cause it helps to get the math facts into the brain. Simple and plain, we educate with minimal strain. Have fun, everybody now, isn't it great? Try some long division today, we just give it away. No time limits, you can...
All right, Stats fans. We are live. Video 39.
Ooh, we made it to 39.
Yeah. So, Mr. Miller's got his fun yellow sheet of paper here. Let's get to it.
All right, it's all in the yellow sheet.
Okay. So, today is least squares. So, Mr. Miller, here we have horsepower and gas mileage in our first example.
Right.
For 2007 vehicles.
No Corollas on there. I'm looking for a Corolla on there.
No.
So the more looks like a negative association, right? So the more
Yes.
horsepower, the faster you can blast off at the corners, the lower the gas mileage.
Yes, that is what I'm seeing as well. So we want to calculate the line of best fit. So remember, in our calculator, these are our x. Yes, these are our x's. These are our y's. So we plug these in L1 and L2. Then we can go into stat calc and figure all that out. And Mr. Miller's already done that for us.
I was going to say, you just consult the magic yellow sheet.
Yeah.
It is y hat
Y hat.
equals negative 0.06
0.06
x
x
plus 33.53.
33.53.
Okay, so
All right, very key to remember the y hat. Don't just put y.
yeah, so y refers to an actual data value.
Yeah, and we want, this is the predictor.
Right.
relation.
Okay, so it says predict the value for a Dodge Dart that has 325 horsepower. So to make a
Okay.
prediction, we just plug in for the x variable. Horsepower is the x variable.
Right. So y hat negative 0.06. Let's make that more of a 6. Times 325 plus 33.53. This was not on the magical yellow piece of paper.
No, this is live, man. This is real math.
Yep,
Plus,
33.53.
yeah, I forgot we didn't do this part.
What do we got?
Okay, 14.03.
14.
So what that means if,
0.03.
based on our data, if a car comes along that has 325 horsepower, we would anticipate gas mileage of 14 miles per gallon.
Yes.
Pretty low. It's about what my minivan gets. All right.
Minivan.
Yeah,
All
no,
right.
It really stinks.
So now we want to calculate the residual. Now the residual, remember, is the difference between our actual value y and our predicted value y hat. So we want to calculate the residual for the Chevy Aveo. Is that how you pronounce it?
I don't know.
Whatever. So that would be this guy right here. All right, there's our Chevy. Okay, so our actual y was 27. Well, we need to find the predicted value. So if we plug in, the Chevy Aveo gets 103 horsepower. So negative 0.06 times 103 plus 33.53
It's pretty close.
is
27.35.
27.35.
So that's predictive. So now we got to
Yes.
do actual minus predicted. Like
Right.
AP stats. Actual minus predicted.
So in this case, our predicted, we kind of overshot a little bit in our predictor.
Mm-hmm.
So it'd be 27.35. So we subtract that. Oops, I'm sorry. That's wrong.
Yeah, this is
27 is first,
yeah.
then minus the 27.35. Okay.
You
So-
get negative
Yep.
0.35. So it's a negative residual, means that it was below the line, so the actual value was less than the predicted.
Yes.
Okay. All right, so we got to know that formula. Residual is actual minus predicted.
Mm-hmm.
Okay,
All right.
what do we got?
So this is just looking at our data. We made this lovely little graphed line.
That is nice.
Uh-huh. And what are we doing with this line, Mr. Miller?
That is not any old line, Mr. Lewis. That's not an okay line. That's not an all right line.
That is our
Beyond fabulous.
line of best fit.
That is the best line.
Yes.
Okay, so 4, we're going to go through again what it means to be best. So we got some pictures for this data.
Okay.
So there's the residuals are drawn.
Yes.
So that's the vertical distances. We drew them in class, and they represent the error, kind of the residual.
Mhm.
So if it's above the line, we know that the residuals are positive because the actual is bigger than the predicted.
Correct.
And if they're below the line, that means the actual is less than the predicted amount, and it's negative.
Mhm.
But when you add those up, they kind of cancel. They're maybe not exactly 0, but since we have some positive numbers and negative numbers, they sort of cancel each other out. So we square them. So hit it, Mr. Lewis. That's what these squares represent.
Yep.
The squares of the residuals. So we're kind of making this like geometry here.
Ooh.
So the area of each square is the area of the square of the residual.
Yeah.
Does that make sense?
That does.
So these are the squared residuals. And we add them up to get the total squared error. And this line did the best it
Oops,
could.
I'm sorry. All right.
All right.
Best we could?
Yeah.
Good? Okay. Sorry,
Okay.
I'm getting ahead of them.
Now, we have some data here. Here's the old hamburger data.
We
where-
love our hamburger
I
problem.
know. I'm hungry for one. So the fat grams is the X, and the calories are the Y variable. So we fit the same data with several different lines. How would you describe the fit of this line, the first one, in the A there?
Not very good.
It is beyond that very good.
Yeah,
It
it's
is
pretty awful.
horrible. It's going the
Yes.
wrong way.
Yeah.
So our line has a negative slope, and the data has a positive association. So we would expect a total squared error that's really, really bad.
Right.
And it is.
And so our magical sheet, what is our total squared error?
73,206.
73,206.
Now, it's actually not the size of the number that matters, it's whether we can make it smaller. And we can actually make this dramatically smaller.
Yes.
Okay, so we had a little program that if you enter the data and the line, it tells you the total squared error
Right.
instead of making a table for it. The next one's a lot better.
Yes.
Still,
At least
how-
we're going the right direction.
Mr. Lewis, how could that line be improved, though? I mean,
Well, see how everything's above the line? We could shift the line. We kind of want like half and half. We want to kind of be splitting the data.
yeah, so that one's just right direction, kind of in the ballpark, but a little too low.
Yeah.
It's better than the first line. The total squared error for this one was 9,300,
9,300.
dramatically smaller
Yes.
than the first one.
So,
Okay. The next one, same data. We're kind of approximating it with a horizontal line. You think this is going to be bad or good?
I think it's going to be bad.
Yeah, it's not as bad as the first one, but it was 48,400. Okay, now this last one is the very best line,
Yes.
and it goes as low as you can go. This one, the total squared error is 3,736.
3,736.
Remember, the first one was 73,000.
Yes, this is almost
The second one was much better, was 9,000 and something, but this one got it down to under 4,000, 3,736.
Mm-hmm.
For this data, that's the best you can get. So that's the one that minimizes the squares. So Lewis, I don't know if you can kind of pencil in a couple squares,
Sure.
but you can see
We
that
can try.
if we drew in the residuals and the squares,
Let's see. Vertical space.
if we drew in some of the residuals, then
I don't know how good my squares are being.
but if we drew in the squares for the total squared error, they're not very big.
No, you can see they're pretty small.
Okay. All right. So the moral, I feel like the Jerry Springer show. The moral of this stats story is the
Yep.
line of best fit is the line that makes the total squared error the smallest.
And a very nice moral it is.
All right. Okay. Next.
All
okay.
right.
Another example of okay versus best. Scatter plot below was made from this data. Okay. And that's an okay line. All right.
Okay.
We're going to compare the squared error from that line with the very best line.
Okay.
Okay, so for the
So-
okay line,
For the okay line, what was our equation?
it was y hat equals 3.12 plus 4.11x. And for our OK line, it really wasn't that bad. The total squared error was 1,038. But we can do better.
Yes, we can.
The line of best fit is y hat
Y
equals
hat equals.
14.69
Oops. 69
plus
plus
2.82x. So that's what our calculator gave us. And the total squared error is a slim 758.9.
758.9.
So even though our first line was okay, it was pretty good, went through the points fairly well, we could do a little bit better with the line of best fit.
Yes.
And so we got to remember, what we're making, what the best means is the smallest total squared error.
Nice.
All right,
All right.
you know what time it is?
I think it's journal time.
It is.
All right.
Ooh, this is the chirping rate of crickets.
What a nice sound that is.
And so it depends on temperature. So I don't know, they crank up the room to like 90 degrees and put a little microphone in front of the cricket and say, all right, buddy, chirp.
That might be worse than waterboarding.
And then they chill the room down to 50 degrees. Poor little crickets shivering. You can only get 20 chirps per minute. I don't know, something like that. And how do you count that?
I don't know. Some guy with very little life. Anyway.
I think they slow it down. They record it and slow it down, so it's like chirp, chirp, chirp.
Anyway, let's just look at the temperature. So these are our X values and then our chirps per minute, our Y values. So
Yep.
find and graph the regression line. So that would be the line of best fit.
You know,
Okay.
my kids chirp more when it's cold.
Use the linear regression to estimate the chirping rate at 100 degrees. So it's not on here. So 100 degrees would probably, if we would estimate it, probably should be a pretty high number.
Yeah.
And then calculate the residual for the 60-degree mark. Okay.
Could you circle that point there?
Yes.
Okay, so that's the actual data point. You can calculate the residual for that. Then, what does the residual tell us about the predicted value for 60 degrees Fahrenheit? Was it predicted an overestimate or an underestimate? It's kind of what we're looking for. All right, best of luck.